So good morning, everyone. Thank you for coming. So today's talk is again some homotopy theory inside of homotopy type theory. So we'll first talk about the James construction, which is a generalization of Freudenthal suspension theorem. So we'll first recall what is Freudenthal suspension theorem and explain this generalization. And as you know, maybe, Freudenthal suspension theorem gives a lot of information about homotopy group of spheres. It gives the stability of some homotopy groups. But it does not allow to compute any kind of homotopy groups. And the James construction is a generalization which will allow to compute some more homotopy groups. And in particular, in the second part, I will show to compute pi4 of S3. So there is, unfortunately, still some computation missing at the end, but you will see. OK, so I first recall the notion of connectedness of a space and of a map, because I will use that everywhere. So take X a type, and n at least minus 2. You say X is n-connected if and only if the n truncation of X is contractible. Okay. Another definition of connected type can be given using homotopy groups. So if n is at least 0, then you have X is n-connected if and only if the 0 truncation of X is contractible. So if you want the pi0 of X is contractible. And for all point X in X, and for all K in 1n, 1 to n, you have pi k of X is trivial. So a space is n-connected when everything is trivial up to dimension n. So all homotopy groups are trivial up to dimension n. And stuff happens after that. So for instance, Sn plus 1 is n-connected, because we know the first homotopy group of Sn plus 1. OK, now if you take a map from X to Y, we'll say F is, so and again, n at least minus 2. We say that F is n-connected if for all y in Y, the fiber of F at Y is n-connected. So F minus 1 of Y is n-connected. So this is the H fiber of the map at the point Y. So there are a lot of equivalent characterization of n-connected maps. Another one is a map is n-connected if it's left orthogonal to all n-truncated maps, for instance. So equivalently, F is left orthogonal to all n-truncated map. So Mike recalled that yesterday in his talk. OK, and another characterization, if n is at least 0, is that F induces an equivalent, an isomorphism between all homotopy groups less than n. So when n is at least 0, f is n-connected if and only if the zero truncation of f which goes from the zero truncation of x to the zero truncation of y is a bijection. And for all points x and x, and for all k between 1 and n, you have pi k of f, which goes from pi k x x to pi k of y f of x, is an isomorphism. Sorry. So for all k less than n, less than or equal to n, this map is an isomorphism. And the map for pi n plus 1 is a surjection. Okay, so it's pretty easy to see that because you can just, using this definition, you can just write the long exact sequence for the map f. You get something with a bunch of 0 in the first column, so you get all these isomorphisms and then a surjection at level n plus 1. So the vague idea that you should remember is that if you have x from x to y and connected, then in some sense x is an approximation of y up to dimension n. So say you want to study some space y, and you know the space x. If you find a map from x to y which is n-connected, then you know basically everything in y up to dimension n, because this is exactly what this theorem says. You know all the homotopy groups of y because they are the same as those of x. And you also know that this is a surjection. Okay. So now, for instance, if we want to study the spheres, we will find some map which goes from some small dimensional sphere to some higher dimensional sphere, which is sufficiently connected, and you will get a bunch of results on the homotopy groups. Okay, so before stating a Freudenthal suspension theorem, I will first recall what is the suspension, because there are several definitions, and I will use both. So the suspension of a space, if you have A a type, suspension of A is defined to be the following push-out. You have 1, 1, and A in the middle. So this is the usual suspension. You have the north pole, the south pole, and then for every point in A, you have a path from the north pole to the south pole. Now there is a different definition which is equivalent, but sometimes it's better. It's called the reduced suspension. So if you take now a pointed type, So usually in topology, the reduced suspension is defined by you take the suspension and you assume A is pointed. So you have some base point here. So you have one canonical path from north to south. And what you do is just you contract this path down to a single point. So here we cannot really contract something down to a single point, but we can do it propositionally. So the reduced suspension of A will be the following higher inductive type. It will have now only one base point, star, which is in the reduced suspension. Then for all elements of A, you will have an element of the loop space of the suspension. So for all points of A, you will get a loop in the suspension of A from the base point to the base point. So if this is the base point and you have A, you have a bunch of loops like that. And then you need to say that what happens if you apply P to the base point of A, you should get the reflexivity path. So you get one additional constructor which says P applied to the base point A is equal to the reflexivity.
But
yep.
When you write omega sigma A, you don't talk about star?
Omega, it's implicitly based at star. There is no other point anyway. Yeah. So if this is your base point, you just add a two-dimensional cell in that. Okay? So in other words, if you look at this definition, you get that sigma A is the free pointed type together with a pointed map from A to the loop space of the suspension of A. Because the constructor, the first one says that sigma A is pointed. This one says that you have a map from A to the loop space of the suspension. And this one says that P preserves the base point. So the suspension basically is just the free pointed type together with a pointed map from A to the loop space of A. Okay? And the two definitions are equivalent. You can write the map back and forth and prove that that the composition is the identity. It's not different. No, but yes, if A is pointed, then the two definitions are equivalent. Because you can, every time you have a path, you can compose with the canonical path going through the base point and get that. Okay?
I think the word together is not good there. Because it suggests you have a three-pointed type and then together with a map. Yeah, no. That's not good.
Yep.
Three-pointed type generated by a pointed map.
Yeah.
You could just remove the together. Yeah. The sentence is as good.
No, it's
Together. Yeah, it's good like that.
well, it's the free thing like that. If you want.
So I mean, S can be also put it as a high inductive type, like 2
Yes.
points and
2 points, and for every point of A, a path between the 2 points. And you can prove that the two are the same. Okay? So when you take the loop space of something, intuitively you decrease the dimension. Everything which was of dimension 1 becomes of dimension 0. So every path, every loop becomes a point. Every two-dimensional loop becomes a one-dimensional loop, and so on. And the suspension is basically we try to do the inverse operation. We take everything which is a point and try to turn it into a path. and everything which is a path in A, we turn it into a two-dimensional path, and so on.
Can you repeat the beginning of the sentence?
For the loop space?
When you take the loop space, you reduce the dimension.
Yes, you reduce the dimension, and here you increase the dimension. So we could ask, do the two operations are inverse to each other? Say, if you increase the dimension and then reduce the dimension, is that an equivalence? So we have this map A to omega sigma A. Is that an equivalence? Because we take A, we increase the dimension with the suspension, then we decrease the dimension by the loop space. We have something which looks like A, but maybe not exactly. So in general, it's not the case. One simple argument is that just the loop space of the suspension has more structure. It's an H space, because you have an operation of composition of paths. And in A, in general, it's not the case. So this map cannot be an equivalence in general. But but you still know something about this map. Which is the Freudenthal suspension theorem. Which says that if A is n-connected, then this map A to the loop space of the suspension of A is 2n connected. So it's not an equivalent, but it's at least more or less the same thing up to dimension 2n. So knowing A, you will still get some information about the loop space of the suspension of A in the range from n to 2n. So in particular, a consequence of that is the stability of homotopy group of spheres. We get that if you fix a natural number k, you get that pi n plus k of Sn is stable for n at least k plus 2. So stable means that they are all isomorphic for every possible n at least k plus 2. So this is a direct consequence of that, because the suspension of Sn is Sn plus 1, and then the homotopy group of the loop space are the shifted homotopy group. So this is a direct consequence of this result. And in particular, for k equals 1, what you get is this stabilized for n at least 3. So you get pi4 of S3 equals to pi5 of S4, pi6 of S5, and so on. So as soon as you know pi4 of S3, you get all the pi n plus 1 of Sn from that. Unfortunately, Freudenthal suspension theorem does not explain how to compute pi4 of S3, because you have A to the loop space of the suspension of A, which is some 2n approximation, but it's not enough to compute pi4 of S3. We need a better approximation of it. And this is exactly what the James construction is about. It's to improve this to give a sequence of successive approximation of omega sigma A, which are more and more connected. Okay, so more precisely, what we'll do is the following. So suppose A is a pointed type. So you have a map from 1 to A. Then I will define some space J2 of A with a map from A to J2 of A. And then J3 of A, J4 of A, and so on. So we'll have a sequence of spaces with map between them, like that. And we'll know two things. First, we'll know the connectedness of all the maps. So if, assume A is n connected, okay, assume A is k connected, then the map from 1 to A is k minus 1 connected. Okay, this is a general fact. If you have a space which is k connected, the inclusion of a point is k minus 1 connected, because the fiber is the loop space, which is k minus 1 connected. Then we'll prove that the map from A to J2 of A is 2k connected. The map from J2 of A to J3 of A will be 3k plus 1 connected, then 4k plus 2 connected, and so on. So the first map is k minus 1 connected, and then for each map, the connectedness increases by k plus 1. And then the second property we'll need is if you take the colimit of this diagram, there is a question? Oh, okay. So if you take the colimit of this diagram, the limit of the Jn of A, we can call J of A, we'll prove that this J of A is actually equivalent to the loop space of the suspension of A. So what does it give? Well, we have a map from every of these guys to the colimit. And moreover, this map, for instance, the map from A to the suspension of A is the so-called transfinite composition of all of these maps. And connectedness is preserved by transfinite composition, because this connected maps are left class, and left class are closed under transfinite composition. So this map is 2k connected. This map is 3k plus 1 connected, and in particular 2k connected, and so on. So you get that this map is 2k connected. So you get, as a consequence, the horizontal suspension theorem. But you get more, because now, if you look at the map from J2 of A to the loop space of the suspension, now this map is 3k plus 1 connected. So you get a map like that, 2k connected, which is just horizontal suspension theorem. But you also get a map J2 of A, which is 3k plus 1 connected. And then a map from J3 of A to the loop space suspension, which will be 4k plus 2 connected, and so on. So you get a sequence of better approximations. And when you want to study some homotopy group of omega sigma A, maybe the first map is not enough, as is the case for pi3 of S2. But then we'll just go to the second map, and we'll need to study this J2 of A and use that to compute pi4 of S3. And of course, we'll have an explicit definition of all this space. So we have an explicit definition of J2 of A, and we'll use that to compute pi4 of S3. Okay? Maybe some intuition on what are those Jn of A. At least topologically, the J of A, which is the loop space of the suspension of A, you can see it as the free group, the free topological group on the pointed space A. Because, well, basically when you add A in the loop space of suspension of A, so every element of A is, of course, in the loop space of the suspension, but you have a lot more operation. You have composition of paths, and you have inverses of paths, and so on. And you can see that what you get is actually the free topological group on A. The problem with that is that it's not clear how to define that in homotopy type theory, because we don't even know what is a group, which is not a set. Yeah?
Just a quick one. So we're assuming here only that K is at least 0?
So in this case, if K is -1, then all the maps are -2 connected, which gives no information at all.
But the limit will not be.
So the limit, yeah, I think we assume K at least 0, because the limit will not be the, yeah.
So as long as you're mentioning the possibility that K is equal to 0, is this potentially useful even for pi n of Sn?
For pi n of Sn, we have Freudenthal suspension theorem gives that that as soon as you know pi2 of S2, you know all pi n of Sn. But I don't know if you can use that to compute pi2 of S2, maybe.
I think the theorem that the loop space of the suspension of A is the free group on the pointed space A is true without restriction on A.
Yes. So this is true without the assumption that K is at least 0. But I will explain just in few minutes why we need why we need A 0 connected at least.
I usually think that this is a theorem of Newton's Milnor, but I don't know about my knowledge of the history of homotopy theory.
I don't. Yeah.
If it's not 0, can.
I'm sorry?
Okay, sorry. Yeah, it's about 0 connects. So -1 connected means non-empty, right?
Yes.
Yeah. So it can still be.
No, pointed. It's pointed.
Yeah, so
It's pointed
so
anyway.
-1 connected.
Yeah.
By assumption. So it can it can be not 0 connected. That thing that definitely holds for any space, for any non-empty space, right?
Yeah, but it's
Yes.
pointed.
This holds for any pointed
So for
space.
any space.
Yeah.
It is very important that the base point of the space becomes the unit of, so it's free but relative to
Yes.
forcing the base point to become the unit of the group.
Yes. So when I say free topological group on the pointed type A, small a, it means that the small a becomes the unit of the group.
So, for example, it's interesting to test it for S0, the zero sphere.
Yes.
Because the suspension of the zero sphere is the one sphere, and the loop space of the one sphere is Z, which is the free group on S0 as a pointed space.
Yep.
Well, the difference is that if it is connected, then you can take the free topological monoid generated by it.
If it's connected.
If
Yes.
it's connected.
Yes, that's the
This is what I'm about to say.
That's where this
Yeah.
J3 things come from, right?
Yeah, this is what I'm about to say.
So
Yeah.
this filtration probably is not defined unless it is connected.
Yeah.
Okay, carry on.
Okay, so
So
we don't know how to say a topological group or something like that, but we can express what is the free topological group. Because the free topological group is just the free pointed space with an action of A by equivalences such that A, so small a, acts as the identity. So if you take the free topological group, every element of A will act on it by multiplication. And this action is an equivalence. And the base point, given that we said the base point should be the unit, the base point will act by the identity map. And so we can use that to define this free topological group, just saying take the free pointed space together with an action of A by equivalences and the proof that A acts as the identity. So with a high inductive type, so maybe I should not call that JA. So I will call that f of A. So we can define it as a high inductive type. So there is one base point in f of A, then one alpha, which is an action of A by equivalences, and something which says that alpha applied to the base point equals the identity equivalence on FA. Okay, so this is not something which is usually allowed in high inductive type, but you can just take your favorite definition of equivalence and unfold it. Like take alpha joint equivalence and you unfold it, you get a bunch of different constructors which are all allowed in a high inductive type. So this defines a perfectly correct high inductive type. And you can prove this result easily. But
Wait, you can prove what?
that it's the loop space of the suspension of A.
Okay.
I will do it in just now.
Did you use equivalence to change those equivalences fast?
You mean
Yeah.
write FA equals FA?
Yep.
Well, it will be an equality in type, not in FA. So no.
Yeah, but it's even more complex.
It'd be even more what?
Well, it has a higher definition and new test to type. Yeah, this one's not good.
So this would be like adding fast to the units?
Yeah, no.
What's wrong with that?
The reason
We don't want to add more.
the reason is work is because you have f of A on both sides. If you have something else, it will not work. You
Definition of equivalence. Yeah, that's what he said.
Yeah.
Okay,
Yeah.
didn't get it. You get a bunch more points and fast.
but now actually if A is 0 connected, we don't need to do that. We can just take the free topological monoid on A. We can just take, so this one I will call it J of A, with one point in J of A, one action of A, which is just a normal action, not by equivalence, and again, a proof that the action of A is the identity map. So if A is 0 connected, you can define that, and you get J of A equals f of A. So you don't need to have equivalences, you just need maps. The reason is that you know that the action of the base point is the identity, which is an equivalence. But A is zero connected. So every point is merely equal to the base point. So every other action is merely equal to the identity action. So every other action is, in fact, already an equivalence. So in the case where A is zero connected, you can prove, you can just use this one, which is the free topological monoid on A. And now we can prove. Yep.
It's the free topological monoid.
It's the free topological monoid in one word.
Oh, yeah, okay.
I haven't defined what is a monoid or a free or a topological. This is just this high-end active type. And so now we can prove that this J of A is the loop space of the suspension of A. So the proof is very easy. If you know how to do pi1 of S1, you know how to do that. So for instance, you define a vibration code from sigma A to type. So you can call it code if you want the type theoretic method, or something else if you want the homotopy theoretic method. And so codes of the base point will be this free monoid J of A. Then when you apply code, I don't know what name I choose, but something like P of A. So the suspension has one base point. Then for every element of A, you have some canonical path from the base point to the base point. I think I call it P of A. So for this, you get alpha of A, which is the action of GA of A to GA, which is an equivalence because we are in the case where A is connected. So you take this alpha A, you prove that it's an equivalence, and then you apply the univalence axiom to get a path in the universe. And then you need some additional constructor which says app of code to the P of the base point is something, but this is just the last constructor which says that the action of the base point is JA, is the identity. And then you can do encode decode or compute the total space and prove that the total space is contractible. This is exactly the same proof as for pi1 or S1.
Theorem, which is not really a theorem because he hasn't bothered to state it yet.
And encode decode.
Mikhailov's theorem, Dan Mikhailov's theorem.
So this is.
Well, no, that's why it's a joke.
So this is like the same thing you would do if you assume that A had an H structure, right?
This is not exactly the same because alpha is just an action of A on J of A.
Okay.
It's not a multiplication on J of A.
Okay.
But well, it's
How does it relate to the Hopf construction that
Yeah.
you spoke about before?
I don't know.
Like if A, is there something like if A has an H structure, then A is equivalent to J of A or something like that?
No, I doubt it because it would mean that every space which has a H structure is equivalent to the loop space of suspension, and this is much more. There is much more structure than just H space
Okay, so
structure.
this is similar.
Okay, so this J of A, you can think of it as the free topological monoid on A. And then what are the Jn of A? Well, Jn of A is just intuitively the subspace consisting of words of length at most n. So for instance, word of length at most 0, there is only one, which is the empty word, so you get 1. The word of length at most 1, you get exactly all the elements of A. You get A, and then J2 of A, J3 of A, and so on, which are words of length at most n, intuitively. Okay? Okay, so now we need to define that. Okay, so for that, we first need some lemma about connectedness of maps, which is basically exactly what Peter used in his proof of Freudenthal suspension theorem. Slight generalization, but basically the same. So first, if you have two maps, F from A to A prime and G from B to B prime, so you have the following diagram. Where each map you apply the identity on one side and F or G on the other side. And you can take the push out of the top two arrows. Take a push out, and then there is a canonical map from the push out to A prime times B prime. So this canonical map, I will write it F star G and F star G. So F star G, wait, I will write it down here. So F star G is a map from A prime times B, push out aim times B, aim side B primes, to A primes times B prime, which is called the push-out product of F and G. Okay, and so now the result is that if F is n connected, and G is m connected, then the push-out product F star G is n plus m plus 2 connected. So as a special case, if you have A, which is a point, and B, which is a point, this is just the wedge of A prime and B prime, and this map is the inclusion of the wedge into the product. And so you get the result that the inclusion of the wedge into the product as the connectivity, the sum of the connectivity of the two spaces. And the proof of this theorem is exactly the same proof as the proof that the inclusion of the wedge into the product is n plus n connected. So I don't think we've ever seen it in a talk, but I don't really have time to do that. So it's been proven in Agda by Dan and in Koch by Peter, so it should be fine.
This is a known thing in topology,
I guess, yeah.
Does it have a name?
I seem to remember seeing it invoked somewhere in one of the proofs.
Oh, you have exactly the is there?
Yep. There are certainly approaches that use things like this.
Okay, so now we can start constructing the James construction. So constructing the Jn of A and the maps between them. So assume you have A a pointed type with the map A naught from 1 to A. So I write J naught of A is 1. And so we will define the following. We'll define, so for n in n, we'll define a space j n plus 1 of A. So we'll define it by induction on n. So for every n, we'll define a space j n plus 1 of A. A map in goes from jn of A to jn plus 1 of A. So if you see that as word of length at most n in the free monoid, then this is the natural inclusion of word of length at most n into word of length at most n plus 1. Then we will need some alpha n of type A times jn of A to jn plus 1 of A. So if you have a word of length at most n and an element of A, you can multiply the two, and you get a word of length at most n plus 1.
This is called cons.
Yes. Except that you go into some monoid with some cancellation and stuff like that. But yeah.
Maybe lists of things are suitable. The free monoid lists form too.
It's the free monoid with the base point being the identity, so you need to quotient by stuff like that.
Right. I mean, like JA has constructors nil and cons, right?
Yes.
Yeah.
Right.
Where's con and could?
And we will need some commutative triangle.
Our further is induction.
Sorry? And we will prove this fact, which is with a formula you have, if you multiply something by the base point, it's the same as doing the inclusion of jn of A into jn plus 1 of A. Okay? So this is our induction hypothesis. This is what we want to prove by induction.
I guess you always define the base point to be ion of the previous base point.
Sorry?
You always define your new base point to be ion of the previous.
We don't need to define a base point.
Just refer to the base point of Jn.
No, it's not the base point of Jn, it's the base point of A. This is the map which sends x to A naught x. Okay, so we want to do that by induction on n. So for n equals 0, we want to define j1 of A. So it will be A. The number one term in the sequence was A. I naught of A should be something from 1 to A.
So why isn't that a definition already? It almost looks like a definition.
Just a recap, a recall of the definition.
What do you mean? I define that by induction on n. So for n equals 0, I need to define j1 of A. I define it to be A.
But you define J naught, and you define it out of step.
No, because in the inductive step, I have n plus 1 and n. So there is some shift in the indices.
Okay, but if you sorry, isn't what you need to define?
I will define jn plus 1 together with in together with alpha n.
Sorry, gotcha.
Yeah, you need the J.
And the j naught is some previous definition. It's a bit strange, but
My question is, why isn't that a definition? I'm just having trouble understanding why we're not done
In what
already.
sense is it a definition? He's stating that's the goal of the induction.
Yeah.
He hasn't said anything about what Jn is yet.
It'll set up the J.
Why
on top.
can't you do Jn plus 1 as a higher inductive with those constructors?
Because we don't want to. We want to give an
because we want something else.
Okay.
Why isn't that explicit?
It's not a definition.
It's not the definition. It's what I want to prove.
What would J1
It's
be?
the type
Where
of the
does it say
definition.
Jn of A equals something or other?
That's not the definition.
No,
It's
we
the
don't want
type
to
of the thing.
define a function from natural numbers to
That.
to the type of triples of this
Shape.
of this shape.
I have not defined jn plus 1 at all for now. I just say jn plus 1 is a type, and there is a map in like that, and there is a map alpha n like that. But I didn't say what is jn plus 1.
If I understand correctly, that's the theorem we want to prove. And this
Yes.
is the definition.
This is what we want to prove, and I'm about to prove it. Okay? So for n equals 0, we need to define j1 of a, which is a, I naught of a, which will go from 1 to a, so we take the base point a naught, and alpha naught of a, which should go from a to a, because you have a times y to a, and we take the identity on a. Okay? Now, I suppose I have all of that for some n. I want to define it for n plus 1. What I will do is the following. I take the push-out product of the base point, so the map from 1 to a corresponding to the base point, with an. That I suppose I already know. So this goes from, so it's not here anymore. So if you look at the definition of the push-out product, you get a map like that.
You've contracted.
Yes.
Across.
This is 1 times, this is 1 times. Yeah. Okay? Now there is a map from that to jn plus 1 of a. So on the first component, you just take the identity of j1 plus n of a. On the second component, you take the alpha n, which is the action goes from a times jn of a to jn plus 1 of a. And you need to check that it works for the path here. But the fact that it works, so this map was some in, and the fact that it works is exactly this commutation, this diagram.
Commutation is propositional, right?
Yeah, yeah. So I have this map. I can define this map. And then I take the push out of this diagram. And the space here, I call that jn plus 2 of a. I call that in plus 1. And I call that alpha n plus 1. So I do have a type jn plus 2 of a with a map from jn plus 1 of a and a map from a times jn plus 1 of a. Okay?
This is the case from n plus 1 to n plus
This is the case from n to n plus 1, except that for j, it goes from n plus 1 to n plus 2.
So you have to recap what you already know. You already knew.
I already know j n plus 1, in alpha n. So this is what I used in this part, j n plus 1, in alpha n. I also know j n. And then I construct j n plus 2, in plus 1, and alpha n plus 1.
And you have to check the equality.
Yes, and I have to check this equality. But if you look, this is just one of the part of the diagram. Like, if you just look at this part, this map is in plus 1, and this map is is the identity followed by alpha n. So if you restrict the commutation of this diagram to the first component, this map is first the identity, then in plus 1. And this map is first you apply a naught and then the identity, and you compose by alpha n plus 1. So what you get is exactly this condition. So we have this condition by induction. Okay?
Diagram needed because of the...
By definition, this is a push out, so we have a commutation. I define it to be the push out. So you have a two-dimensional cell in between by definition of the push out.
So where did the wedge into the product come up here?
So not yet.
Not yet. Okay.
But this is when we will compute the connectivity of this
Yeah.
map.
Okay, good.
Okay? So now we can...
I have a question.
Yep.
Suppose we convert your advertisement on the top board into an inductive definition, then would
This?
it turn out to be the same as this construction you just gave, so that we could view this construction you just gave as a computation of that universal one?
No, because you don't get that. If you just take jn plus 1 to be, say, the sum of these two spaces, then you don't get
And even if
what you want.
impose that equality that you've written there,
Yeah.
that's not enough either, right?
You would get it if you use the conditions that you.
Oh, I see. There are more conditions to, some relations were forgotten.
Yeah, yeah.
On the
Yeah.
top board.
There will be some more relations.
That's the point. If you do
Well, I
algebra,
think you
but
have
if
to
you do
write some of the equations that they need.
sense of algebra, it's obviously easier to do.
Couldn't you just write the equations that you get from this?
One equation.
Yes, so you can get the other two equations.
Yeah, there has to be a state difference, but it's stopped.
So you can write the other coherence condition corresponding to the second argument. So this is alpha n. This is the identity. Sorry, no, this is 2. This is in plus 1. This is the identity times in. And this is alpha n plus 1. So what you get is something like alpha n plus 1 of a in of x equals in plus 1 of alpha n ax. Okay, so this is the other coherence condition that you get when looking at the factor on the right. So if you take x, you see it as something with of length once more, and you multiply by a. You could just first multiply x by a, and then increase the dimension of x. Okay? And you need another condition coming from this factor, which is that if you have alpha n plus 1 of a naught and in of x, you will have two different ways to reduce it. So you can either say it's in plus 1 of in of x using this equality. Or using that, you say it's in plus 1 of alpha n a naught x. And then this is equal to in plus 1 of in of x. So using the two equalities, you have two different ways to prove that. And there is a two-dimensional cell inside that. And the two-dimensional cells come exactly from this factor above in the push-out. So now I think that if you say you want Jn plus 1 with in alpha n, this condition, and this commutation, then it defines Jn plus 1 uniquely. Okay? Okay, now we can compute the connectivity of the map. Because what we want is in is k minus 1 plus n times k plus 1 connected. So this is what I said at the beginning. For n equals 0, you get something k minus 1 connected. And when n increases by 1, the connectedness increases by k plus 1. So to prove that, it's actually very easy, because I naught is a naught by definition. And this one is k minus 1 connected, because we assume that A is k connected. And then in plus 1 is a push-out of the push-out product a naught in. And taking a push-out of n-connected maps gives an n-connected map. And we know the connectivity of that. It's exactly the connectivity of in plus the connectivity of a naught plus 2. So you get this k plus 1. That's because n-connected maps are left orthogonal to n-truncated maps, and left class are preserved by push-outs. Okay, so what we have so far is the following. We have this sequence of spaces, and we know that this map is k minus 1 connected, this map 2k connected, this map 3k plus 1 connected, and so on. The only part missing is that the colimit of this diagram is the loop space of the suspension. But we've already seen that the loop space of the suspension, in the case where k is at least 0, so when A is connected, we've seen that this is the free monoid on A with a base point. So the only thing we need to check is that this colimit has the same universal property as the free monoid on A with a base point. So we need to check that is the free topological monoid on A pointed.
Why do you write topological there?
Because, well, this is just one word. If I say free monoid, we don't know what monoid means. At least when with topological, we even less know what it means. This is what I defined earlier. If I say free monoid, you may think of monoid based on set. At least here you can't.
By free topological monoid, you mean the free space with an active
Yes. So I mean this JA with one base point, one alpha, one action, and something which says that the action of the base point is the identity map of GA.
Type monoid? You could just omit the word since we're in type theory and everything's topological.
Well, no.
Omit the word monoid and avoid this whole worry about that and call it an A space or something.
Monoid. Oh, it's monoid. I think it's
The free monoid, I mean, it's just
It's
that,
the free infinity monoid.
So
And
you
monoid
should-
might mean a
there's
set.
nothing in
And its definition does look like a definition of monoid because there's no operation.
That's possible before.
no, but
So it's probably maybe close to what they
you know it's a monoid.
Where
It's
does
just that we are not proved it, but distinctly.
It's something you define yourself, or you found it in the literature somewhere?
Zero monoid.
Which one? That?
The free topological monoid.
So this is something we can define in topology.
Why do you call it
Yeah.
J prime? And
Yeah.
say that this is the limit of the J prime construction.
So we can call that J of A. And we want to know if this satisfies this condition. Okay, so to do that, we need to define the various constructors on the colimit and define the dependent eliminator. So prove that this limit has exactly the same dependent eliminator, and then we'll be done. Okay, I will put primes everywhere. Thank you. So I need to define a base point in J of A, but this is easy because it's a colimit and J0 of A is already a point, so this J of A is as a base point. So yeah, maybe I could recall. What is the colimit? The colimit says if you have n in n and x in Jn of A, then you have something called nx in the colimit, and moreover nx is equal to n plus 1 in of x, because this is the maps from Jn to Jn plus 1. So we need to define a base point in Ja. So this is easy. We just take 0 and the unique element of J naught of A. So J naught of A was unit, so it's called TT in some programming languages, or star, or whatever. The unique point of the one-point space. Okay, and then we need to define this action. We need to prove that the colimit of the Jn of A has an action on, of A. So we'll do it by induction on the second argument. So alpha A and x. What is that? So A is in A, x is in Jn of A. we can consider alpha n of ax. So we already have an action of a on jn, which lands into jn plus 1. So we can define alpha like that on the canonical elements of j of a. But then we have to prove that this is invariant by this equivalence relation. So we have to prove that alpha a n plus 1 in of x is equal to alpha a n of x. Because this is a high inductive type, we need to define it for the point and then prove that it works for the path as well. But we can just unfold the definition. This is, you apply the definition, this is n plus 2 alpha n a in of x, just by applying the definition. And then somewhere we have an equality for that. So alpha n of, this is alpha n plus 1, sorry. So this alpha n plus 1 a of in of x is in plus 1 of alpha n a of x. Oh, sorry, sometimes I put parentheses, sometimes I don't. So using the equation above, you get that. Alpha n plus 1 of a in of x is in plus 1 of alpha n a x. But now, using this equality, this is n plus 1 alpha n a x, which is exactly alpha of a and x. So you get a map from a to ga to ja. Okay, then you need to prove that you have this property, and you need to construct the dependent eliminator and all of that, so I will not do it here. But basically, it's already the same. Just by induction on ja, you reduce to the case of canonical elements like that, and then you use the various commutation properties of alpha n and in, and you get the result. Okay?
Just need those axioms that you wrote down here in the proposition.
Yes.
You don't go back to the construction, just use this axiomatic description.
Yes, the two axioms plus the commutation of this diagram is equivalent to the definition of jn plus 2, actually. So yes, you just need that.
So that shows that the axioms are complete, right? Because they suffice to characterize something with a universal property.
Yeah. Okay, so I have what I said at the beginning, that this colimit is the loop space of the suspension of A. And in particular, this map is 2K connected, because it's a transfinite composition of 2K connected map. This map is 3K plus 1 connected, and so on. Okay. So now let's see how it gives some information about pi4 of S3. So we will apply this to the case A equals S2, and we have K equals 1. because S2 is 1 connected. So what we get is the following. We have 1, S2, then some J2 S2, J3 S2, and so on. And the loop space of the suspension is just the loop space of S3. Moreover, we know that this map is 0 connected. This map is 2 connected, because k equals 1 to k. This map is 4 connected, and so on. 6 connected, 8 connected. And we have a bunch of maps like that. So in particular, we know that the map from S2 to omega S3 is 2 connected. Which means that the best we can get from that is that pi2 of S2 is equal to pi2 of omega S3, which is pi3 of S3. So from that, we get that. So this is the fundamental suspension theorem. So we get the stability result that once you know pi2 of S2, you know all pi n of Sn for bigger n. But if you look at the pi3, the two connectedness of this map just tell us that we have a surjection from pi3 of S2 to pi4 of S3, but does not give any other information. So we know that pi3 of S2 is Z, so we know that at least pi4 of S3 is a quotient of Z, but this map does not give enough information. But now we can look at the other map from J2 of S2 to omega of S3. This map, this time, is 4 connected. So in particular, we get pi3 of J2 of S2 equals pi3 of the loop space of S3, which is pi4 of S3. So now we have a better approximation of omega S3. So we just have to compute this pi3 of J2 S2, and we get pi4 of S3. Given that it's 4 connected, we also have pi4 of J2 S2 equals pi5 of S3. But I don't know how to compute pi4 of J2 of S2, so it's still not enough. But so what we'll do now is to try to compute pi3 of J2 S2, and it will be equal to pi4 of S3. Okay? So what is J2 of S2? If you just unfold the definition, you can see that J2 of S2 is the following push out. So you take S2 times S2. You have the inclusion of the wedge into the product, so correspond to the two axes of S2 times S2. And you identify the two axes together. So if you want to see that as word of length at most 2, what is a word of length at most 2? It's 2 elements of S2, such that when one of them is the base point, then it collapses to one single element of S2. Okay?
So this is a 4-dimensional game. If you do it with S1, then you could try to visualize it. So that means you're gluing together a longitude and the meridian
Of the torus, yeah. Okay, so we need to compute the pi3 of this pushout. Unfortunately, we don't know, there is no formula or stuff like that for pi3 of a pushout, so we need to do some work to do that. Okay. The first thing we will do is try to understand this S2 times S2. Try to decompose it in something else. So the proposition is the following. There is a map from S3 to the wedge S2 wedge S2. Such that S2 times S2 is the following pushout. The pushout of S2 wedge S2 with 1 along S3. So a way to understand that is that you have S2 wedge S2, so a wedge of 2 spheres, and this is just gluing a four-dimensional cell onto S2 wedge S2. So
For example, if we take 1 instead of 2, that would say that the torus is obtained by gluing a 2 cell to a wedge of 2 circles.
Yeah.
Yeah.
Okay. So in topology, this is very easy to prove, actually. So in topology, you can do the following. You say, what is S2? S2 is a CW complex with 1 0 cell and 1 2 cell. Okay? Hence, S2 times S2 is again a CW complex with 1 0 cell. So when you have 2 CW complexes, to take the product, you just take the product of cells. That's very easy. So you have 1 0 cell, you have 2 cells, and you have 1 4 cell. So your 0 cell is a point. The 2 cells, there is only one way that they can be glued to the point. So you get a wedge of 2s2. And then you have 1 4 cell, which has to be glued along this thing. So there exists a map from S3 to the wedge, which is the attaching map, such that S2 times S2 is this pushout.
Confuse cells and spheres here. So
Here I'm in topology. So
The sphere is the boundary of the four.
the sphere is the boundary of the 4 cell. So the attaching map is a map from the boundary of the 4 cell, which is S3, to the n-1 skeleton.
that means that one there on this is the other side of the wedge.
Yeah. So this is very easy to do with CW complexes. Unfortunately, it uses the fact that, for instance, the boundary of a 4-dimensional disk is a 3-sphere, which is not at all homotopy invariant. So we cannot do the same argument in homotopy type theory. But there is a way to do it anyway, which is
That's an interesting
Yep.
situation because
Yep.
there's a place where homotopy type theory and auxiliary homotopy theory are kind of different, and it would be nice to bring
Okay, so how can we do that anyway? So we will use the same very nice lemma that I used last time about you take a 3x3 diagram and take push out in one direction and in the other direction, and you get the same thing. So let me first write some diagram. Then we'll check that it gives something interesting. Okay, so what are the maps? This is the first projection. This is the first projection. This is the first projection. This is the second projection. Then this is the identity. This is constant to the north pole. This is constant to the south pole. So I define a diagram like that. You have pi1, 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 pi2, the identity, two constant maps. So we need the diagram to commute. Those three squares commute definitionally. But this square does not commute definitionally because north is not equal to south. So we need to add a two-dimensional cell alpha here. Oh, wait, continuing this side. So there are many ways to prove that this diagram commute. There are many different propositional equalities. Okay, maybe I can write. No. So alpha goes from S1 times S1 to north equals south. So now I'm seeing S2 as the suspension of S1 with this north and south presentation. And the map we'll take is alpha of x, y is the meridian corresponding to y. Okay? So I have a 3x3 diagram which commutes. One of the commutation is just propositional, but doesn't matter. And the idea is that we take the push out of all the rows and the push out of the resulting column. It will be equivalent to the push out of the columns and then the push out of the row. So what is the push out of the first row? For the first row, you have S2, and then you have a point, and you have a circle of paths between the point and the north pole. The north pole should be above. So what you get is S2 wedge S2. What is the push out of this line? This line is the join of S1 times S1. And in my talk on the up vibration, I proved that this is the double suspension of S1. So this is the three-sphere S3. And what is this one? This line is just a cone on S1. So this is just contractible. This is a point. Okay. Now, what are the push out of the different columns? Okay, the push out of that is S2. What is the push out of that? You have S1 times S1, and then S1, S1, but both pi1, not pi1 and pi2. So actually, this diagram is just S1 times the right diagram. And so this is just a product of S1 with the suspension of S1. And product commutes with push out. So what you get is S1 times S2. Okay? And the map you get in this direction, given that you have a pi2 here, it's just the identity on S2. It's just a projection here. And now what is the push out of this diagram? You have S2, and you glue a circle onto a point. What you get is just S2. Because you have S2, and then you do something like that. Basically. And now what is the map here from S1 times S2 to S2? Well, the north pole is sent to the north pole, the south pole is sent to the south pole, and when you are in between, you are some y here in S2, you are sent exactly to the meridian corresponding to y. So you can prove very easily in type theory, just by an induction on this argument, that this is again the second projection. And then what is the push out of this diagram? This diagram is again the diagram for the suspension of S1 times S2. So the push out of that is just S2 times S2. So we just define the map from S3 to S2 wedge S2 such that this push out is S2 times S2. Okay, I'll try to finish soon. Okay. So now what we want is to study this J2 of S2. So J2 of S2 was the following push out. So now I can replace S2 times S2 by the expression I have above. So S2 push out, S2 wedge, S2. One. So I just replace S2 by S2 times S2 by the expression above. And this map, you can just check in the construction that this map is exactly the map, the natural map from the wedge to the wedge. So you can move the parentheses and get this push out S3 1. But now what is this push out? You just have S2 and you glue S2 times S2 along some identity map. So this one is actually just S2, this part. So what you get is J2 of S2 is equal to the push out of S2 and 1 along S3 for some map here from S3 to S2, which is this map from S3 to the wedge composed with the co-diagonal from the wedge to S2. Okay. Okay, so let's call this map F. So F is the map from S3 to S2 that we constructed in this proof. So what you can prove, so if you look at pi3 of F, goes from pi3 of S3 pi3 of S2, just a map from Z to Z So pi3 of f is just the multiplication by some number for okay. If you have any map from S3 to S2, take the pi3, you get a map from Z to Z, which is a morphism of groups. And you look at the image of 1, you get some n. And this map is just multiplication by n. Okay, I need to use some more non-trivial argument. So this square is the definition of J2 of S2 as a push-out. Now you can take the pullback of that. You get something like that. Okay, so if I call F this pullback, so this is the fiber of the map from S2 to the J2 of S2. And if you write the long exact sequence for the map S2 to J2 of S2, what you get is pi3 of J2 of S2 is equal to Z quotiented by the image of the map so it's Z quotiented by the image of this map. Goes from pi3 of F to pi3 of S2, F2. So this is just, when you write the long exact sequence, you get exactly that. So what we need to understand is what is the image of this map. But now we can use the Blacker-Massey theorem. So Blacker-Massey theorem says that this map is 2 connected, and this map is 0 connected, because every map from S3 to S2 is 0 connected. It's easy to check. And Blacker-Massey says that the canonical map here is 2 connected. In particular, it's a surjection on the pi3. And we are interested in the image of this map. But given that this is a surjection, the image of this map is exactly the image of that map, which is pi3 of F. And what is the image of pi3 of F? It's exactly nz for this n. Okay, so what we get is that pi4 of S3, which is pi3 of J2 S2, is equal to z mod n for this n. And this is one very concrete and non-trivial example of why we may want to have canonicity. Because this n is a closed term of type z, defined with a lot of univalence and higher inductive types. So in a perfect world, if you formalize that in a proof assistant with a computational interpretation of univalence, yep.
So 4 of S3, but it's right you have nz. What is it?
Yeah, that's what we're talking about.
Yes, so the n is the image of 1 by this map. So if you look at everything which I used and everything in this proof, you get a closed term of type z using a lot of univalence and a lot of higher inductive types. So if we add the proof assistant with a computational interpretation of univalence, and you formalize all of that, you can just ask what is the value of n, and you will get 2.
Maybe.
Sorry?
Did you get it?
Maybe.
Maybe. I hope you will get 2.
What did you get it?
Well, we don't have a proof assistant with these properties yet, so we can check now.
So do you have another way of finishing the proof?
So no.
Do you know in principle that you could eliminate everything that every use of?
Well,
No, you don't.
this is exactly the content of the
No, but
conjecture.
For this particular case.
For this particular case, you can define this map. You have this map from S3 to S2. We also have the up map, which is the generator of S3 which is another map from S3 to S2, which is the generator. And you can define 2 times the up map as a map from S3 to S2, and then it should be enough to just write down the 2 maps and check that they are homotopics. This map is homotopic to 2 times the up map. But the computation are quite complicated to do, so I haven't really managed to do it.
There's some non-trivial high inductive types in the construction.
Yeah, there are a lot of non-trivial high inductive types.
And that's where it's not clear what happens.
Well, maybe you can, I mean, it's cheating a little bit. It only works for 2, I suppose. Well, you can maybe prove that the element which you get in pi4 S3 is not 0 by one method, and then try to prove that twice this element is 0 by another method.
So I think proving that twice the element is 0 is not very difficult, but proving that this element is not 0 seems much more complicated.
Well,
Good.
I mean, a modern homotopy theorist would probably do it using, well, that is not 0. Okay, let